Troubleshooting Windows systems that don't boot or perhaps have error messages during the boot is something that you might have dealt with. And while it may be expedient to reinstall, in some cases, being able to determine the phase of the boot process it's failing and perform some minor adjustment might get the system up and operating more quickly. Now, some of the symptoms that you might encounter: error messages that might appear either during the boot process or during the logon process, perhaps crashes, blue screens, spontaneous reboots, system restarts that don't have any record of a crash dump, and also hangs, system freeze-ups, lockups. Also could be error messages during the logon process. These are some of the kinds of issues we're going to discuss in this program.
So the goal of fixing boot problems is identifying the root cause so that you can deal with it. Either remove the component that's causing the problem, update it, fix it, reconfigure it. And some of the common causes of boot-related problems include third-party drivers that are crashing during the boot, applications that interfere with the logon process, files that are corrupt on disk, system files like operating system files, driver files, or data files that are used by the operating system to guide the boot. And malware and viruses are more and more becoming a common reason for the systems to become unbootable or unstable during the logon process.
Now, as I mentioned, it might be the right solution to reinstall, and that is certainly a reasonable approach, especially in an environment where you have disk images that can be quickly laid back out onto a client or server system. But in some cases, a lot of time and effort has gone into preparing a system, setting up application settings that is not so easy to repeat or reload. So in that case, if you're able to isolate the problem causing the error message or the hang, being able to perform a surgical repair might be a more expedient approach. So really the key to being able to troubleshoot boot and startup problems is understanding the boot process and the available tools to address issues during the boot process. So we're going to discuss in the remainder of our program first the boot process, the various steps that Windows goes through from when you press the power key all the way up to logging on. Then we'll look at the main recovery mechanisms provided by the operating system and also a third-party tool written by Mark called ERD Commander that provides some advanced recovery capabilities not possible with the built-in mechanisms. Finally, we'll look at a number of symptoms that can occur during the various stages of the boot process and what the solutions, or at least the plan of attack, could be for trying to isolate and repair problems during the startup process.
Understanding the boot process really begins first with understanding some of the terminology that Windows uses to describe some of the files and volumes related to the boot. Really, what you're going to see here is some of the worst computer terminology ever created. And that's, if you're familiar with computers and terminology associated with computers and software, that's a very big statement to make, but I think once you see the definitions here that you'll agree with me. The terminology I'm talking about is the description of the system volume and the boot volume that Windows uses. The system volume is the label that Windows places on the volume that includes the boot files. And boot files include things like the master boot record, boot sector, the operating system loader, whereas the boot volume is the volume that Windows labels for the volume that contains the system files. It's where the Windows directory is located and the associated files underneath there, like the operating system image and system DLLs and executables. So really, the system volume contains boot files, the boot volume contains system files, the complete opposite of what you would really expect sane terminology to dictate.
Now, the boot process actually begins when you run Windows Setup. So part of the job of Windows Setup is to lay down some foundation information on the volume that will allow the boot process, the various phases of the boot process, to discover the system, allow collecting various options that affect how the system will start and operate, and then proceed to load the necessary drivers and start the necessary processes. So if you look at this graphic here, we've got 8 major steps that we're going to examine, starting with the master boot record, followed by the boot sector, the NT bootloader, the operating system's initialization, then the first user mode process, the session manager, the windowing system, the logon process and its associated security server process, and service startup. So let's take a closer look at each of these phases, starting with the master boot record.
The firmware of x86 and x64 hardware platforms is programmed to read the first sector of the active disk, or the primary physical disk on the system, into memory and begin executing some code placed in that sector, which is called the master boot record. That code is programmed to read what's called the partition table, which consists of 4 entries that can describe the location of volumes on that primary physical disk. One of those entries in the partition table is marked as the active partition, which in other words is giving it the label the system volume, and the master boot record code is programmed to go find the first sector of that volume and read it into memory and start executing it, that first sector being called the boot sector.
Now the boot sector is the first piece of NT operating specific code involved in the boot process. It's NT specific because it has enough code in it to understand the NT file systems that are supported, for example FAT, FAT32, and NTFS. It's a primitive file system in that it's read-only, and it only understands enough to read, locate, and read the root directory of the volume, and locate and load a single file into memory called the NT bootloader, NTLDR. Now we can see the NT bootloader, the file that's opened by the boot sector code. If we bring up a command prompt, go to the root of the system volume, which on this system also happens to be the boot volume because the Windows directory is there, and if I do a directory with the switch /A:/H for looking at hidden files, NTLDR, there's the NT bootloader that the boot sector is responsible to open and read into memory.
The first job of the boot sector is to switch the processor from 16-bit mode into 32-bit mode. All x86 and x64 processors boot into a 16-bit mode for backward compatibility with older operating systems such as DOS. It also turns on the paging hardware. Now that doesn't mean that virtual memory is fully enabled in the sense that we think of when Windows is up and running. There's no paging file at this point. There's simply a virtual memory that maps virtual addresses directly to physical addresses so that the system can access all of the physical memory present on the system. At this point, NTLoader also checks for the presence of ntbootdd.sys in the root directory of the system volume. This particular file will only be present under special circumstances, and those circumstances are that the system volume is on a different disk than the boot volume, and that boot volume is a SCSI disk, which is a pretty uncommon scenario in client systems, more common in server systems. And the reason why NT looks for this file in that condition is that the firmware of the heart of these PCs is programmed only to be able to understand how to read from the primary physical disk. SCSI disks require special drivers to interpret and send commands to the SCSI hardware, and if the disk that the boot volume's on is a different disk and a SCSI disk, Windows during the boot process needs to use the aid of a driver in order to communicate with that disk. The next step of bootini is to, or NTLoader, is to read boot.ini from the root directory of that system volume. This is a text file up through Windows Vista that contains a list of the operating systems present on the machine along with their associated boot parameters. If there's more than one choice at this point, you're presented a menu and can make a selection, and typically boot.ini contains a default timeout value and a default selection, so if no user is there to type a key, it'll automatically continue with the boot. And it's at this point, once you've made a selection, that NTLoader looks to see what type of operating system you've selected to boot from. If it's a 64-bit Windows installation, it's at this point that the switch from 32-bit mode to 64-bit is made. Up to now, the boot process for 32-bit systems and 64-bit systems is the same, and what this makes possible is a side-by-side installation of 32-bit Windows and 64-bit Windows on 64-bit platforms.
Now, NTLoader at this point pauses briefly to allow you to specify or press a special key to stop the boot process and allow you to make special boot selection options. And let's take a look at that special boot options menu. We're going to switch over to a virtual machine where we've paused the boot of a Windows system. We're going to resume that virtual machine. So here we see the special boot options menu that was raised by pressing the F8 key during the boot process. And we'll be discussing safe mode, we'll be talking about last known good, and also touching on debugging mode. Once you've made a selection on the special boot options menu, NTLoader proceeds to perform BIOS hardware detection. And that means running a program called ntdetect.com. ntdetect.com is another hidden file in the root of the system volume. So if we go back to the command prompt, we can do a dir/A:/H ntdetect.com and see this program located in the root directory. NTDetect.com stores the information that it finds about the basic hardware configuration in memory, and later when the registry is initialized, this appears in the registry key HKey local machine hardware description. And if you go to the registry editor, you'll see some basic information about the CPU type and other BIOS detected hardware devices.
Now, speaking of the registry, this is the point where the operating system loader reads in the system hive part of the registry, which maps into HKey local machine system once the machine's up and running. It reads in the system hive at this point because there's a lot of information in there that helps guide the boot process. There's operating system configuration information, as well as the configuration of drivers that the system needs to start up and get the system booted. These types of drivers that have to be loaded into memory by the operating system loader at this point are called boot start drivers, and they're identified with a certain start values we'll see in their driver configuration keys in the registry. The reason that operating system loader needs to load these things, and the system can't simply wait until the kernel's up and running for the kernel to go load them, is that these are drivers that have kind of a chicken and egg problem. If the kernel had to load them, the kernel would need to use the surfaces of these drivers themselves to load themselves, and that kind of cyclic dependency is broken by the fact that the NT loader here gets them into memory so that they're ready to go when the operating system wants to turn them on. After getting those drivers loaded and the operating system itself, ntosKernel.exe, the HAL, and a couple of other core operating system files that need to be present in memory, NT-loader calls into the main entry point of ntosKernel, and it basically to hand off control and get the operating system boot started.
It's at this point that the splash screen appears. So if you see the Windows XP logo fade in, or the Windows Server 2003 logo fade in, you know that you've gotten past the bootloader, and NT-loader has passed control onto the operating system. The Windows kernel now proceeds to prepare itself in two phases. The first phase is sort of the foundational phase where the system calls key functions in the major subsystems like processes, threads, memory manager, I/O system, security, and so forth, for basic data structures to be set up or prepared for use. The second phase, which is actually called phase 1, is when these internal executive subsystems are called to actually create objects and begin execution of the core support mechanisms in the kernel. Part of that phase 1 initialization is then to invoke the drivers that were loaded by the bootloader that were labeled as boot start drivers and ask them to initialize. So this is obviously a point where the system could have a failure. If a boot start driver malfunctions, there could be a blue screen at this point. After the boot start drivers are initialized, then the I/O system goes to reference the registry again and look for which drivers are marked as system start. It's at this point that system start drivers are read in from the disk and also initialized, which means it's another point that drivers during this early part of the boot process could cause a system failure or hang. Finally, when the kernel has finished the phase 0 and phase 1 initialization, all of the boot and system start drivers have been loaded and initialized. The operating system's kernel initialization is complete, and it goes to create the first user mode process that you'll see in the process list, and that is the Session Manager, or SMSS.exe.
Before we talk about Session Manager, let's stop and take a look in the registry at the location where Windows drivers and services are configured. All drivers and services have a registry key under the area HKey local machine, system, current control set, services. If we look at it here on this system, we can find, for example, a registry key that corresponds to one of the Windows drivers installed on this machine. The way that we can recognize it as a Windows driver and how Windows recognizes it as a Windows driver is its type value over here on the right side. A type value of 1 or 2 designates it as a Windows driver. Any other type would be that for a Windows service. And so if I scroll down a little bit further, here's an example of a Windows service, the Alerter service. And if we look at its type value, it's 32 decimal 20 hex. Because it's not 1 or 2, Windows recognizes this as a special type of Windows service.
Now, another attribute of each service in the registry is when the service should be started. And again, service applies to both device drivers and user mode services that we'll talk about later in the boot process. There are 4 basic start types. 0 is a boot start driver. 1 is a system start driver. We discussed when those drivers are loaded. It's the NT bootloader that loads boot drivers and the kernel that loads system start drivers. Automatic start drivers are started much later in the boot process by the service control manager. There's also a type code for drivers that are marked as manual start. And most plug-and-play drivers have a start type of manual because they're loaded by the plug-and-play manager as devices are discovered. Bus drivers are used to enumerate devices on I/O system buses, and the I/O system then, working with the plug-and-play manager, loads and calls those drivers to initialize. Also, drivers can be marked as disabled, and that's a way to force a device that may be causing problems not to be loaded or initialized on the system. There's one exception where the start type is ignored, and that's for the file system driver for the system volume. That's the volume that contains the boot files, or is it the Windows files? The system volume is where the boot files are.
Right.
Even I have trouble remembering the terminology. And it kind of makes sense that the file system driver for the system volume needs to be loaded because that's what the system is going to use to continue to initialize the system in that earlier part of the boot process.
There's a few different tools you can use to look at the start order. And what I mean there is the start order of the drivers that are statically configured to start at various places during the boot process. As Dave mentioned, plug-and-play drivers will have a start type of manual, and so it's really difficult to know when exactly they're going to start up. It depends on the way that hardware enumeration takes place during the boot. But for those drivers that have statically specified start values, one of the tools you can use to look at the relationship between them in the startup order is load_ord from sysinternals. I'm going to launch load_ord by going to the sysinternals folder here and selecting it. And what this does is just simply scan the registry, looking at the startup information, and calculates itself what order the I/O system would start these drivers up. So the broadest category here is the start value on the left, and we're looking at the startup order of various boot start drivers. These next couple columns are the group name and tag, which device drivers developers can use to control their order within a boot phase or within a group, which is what the tag does. And the group name itself would be shown next, followed by the display name of the particular driver.
And something else, Mark, that can affect the start order of statically defined drivers would be dependencies. Some drivers are defined to depend on another driver or service, so that would also override some of the static definitions that we talked about.
Another tool you can look at to see the startup ordering or startup configuration of drivers without having to go into the registry and look at it there yourself is MS-Info32. MS-Info32, under its software environment, system drivers location, lists all of the drivers configured on this system along with their start type, which we've got to scroll over and see, their start mode. So this shows you the broad category here: boot start drivers, disabled drivers or in services, manual drivers, and system drivers. And finally, another tool that you can use is driver query, which is built into Windows XP. Specify this /vswitch, and this basically is the command line equivalent of what we just saw in MS-Info32.
Now, we were up to the point that the operating system completed the kernel initialization and had created the first user mode process, the session manager. The session manager is responsible to perform early system initialization that can be done from process context, and it is going to be also the father of the remaining system processes that are started following its birth. One of the places that the session manager looks at is a registry key that we're going to go to under HKey local machine, system, current control set, control, session manager, matching the name of the process. And this is an interesting key because it has a number of registry values and subkeys that contain early operating system initialization information. For example, one of the things the session manager does is initialize the paging files. And you can find that underneath the memory management key. There's the list of paging files and their size. For example, on Mark's system, he's got a single paging file on the C volume. We see its minimum and its maximum size in kilobytes. The session manager also runs any programs that have been configured in the boot execute key. So let's go back to the registry editor and find that boot execute key. It's actually a value underneath Session Manager. And if I double click on boot execute, we can see that there's one entry, and this is an entry that you're going to find on your system, and that's a reference to the AutoCheck program. AutoCheck.exe is a native image. A native image means that it's calling Windows native services, because at this point the windowing system has not been initialized. It's calling undocumented system calls in the NT kernel to perform a check disk. And every time you boot Windows, the Session Manager creates a child process to perform a check disk. Now, you'll only see evidence of that if check disk finds problems, and you've probably seen during the boot process, if you're on XP, on the blue part of the screen in the middle, some text output might come from check disk. On Windows 2000, it was in a black area in the middle of the screen. So that's text output coming from this boot execute program. Now, this is a place potentially that malicious code could insert itself, and I think this is one of the places you've added in your auto runs tool that we're going to use later, that if something was inserted into there, you're going to see that as one of the auto start locations. It's
right. The number of places that a malware is finding to insert itself in the boot process is surprising and always expanding. But another job of the session manager is to process what are called pending file move and rename commands. And there's a number of files on the system that just can't be replaced while the system's up and running. An example is a core system DLL, like kernel 32, which is going to be mapped into the address spaces of all of the processes running on the system. You can't replace an in-use image file like that, and so servicing, like hotfixes and service packs, has no choice but to perform the replacement the next time the system boots before those files are in use. And they can do so very easily using a standard Windows API called moveFileEx and specify that they want the move or delete operation to take place the next boot. Session Manager is actually responsible for honoring that. Session Manager looks in the registry to see where the pending file move and rename operations have been registered. And
so I think you were telling me, and it is, I've done this now every time a hotfix is installed, or I install any kind of third-party application, and I get the message your system now needs to be restarted, it's easy to see why, because the restart is happening because entries have been made in this pending file move or rename key. So I now go to the sysinternal's pen moves command, run that just to see what files couldn't be replaced during the installation of the program that I just completed.
And what I've done is run pen moves after I installed Windows XP Service Pack 2 to look at the number of files that Service Pack 2 had replaced and required a reboot in order to finish the replacement for. And that file is here in XP SP2 penmoves.txt. And if you look at it, you can see the output of pen moves. For example, this first line in that output says that the source of the move is this temp DLL and that it's actually a delete operation. So we can surmise that what's happened here is that the service pack has has renamed the currently used file, the one prior to the service pack, to this temporary name, dropped down the new version in its place, and then scheduled the deletion of this old copy at the next reboot. The number of, by the way, file replacements in Service Pack 2's update that required a reboot in order to complete the replacement you can find using a word counting utility. So I'm going to run this through word count, and each line in that file, or each entry in that file, it takes up 3 lines. So if we take the number of lines in that file, 1,200, and divide by 3, we get a rough estimate of the number of pending file move and renames. Comes out to about 400.
Well, XP Service Pack 2 was a
hefty release.
Hefty service pack, and a great service pack, I must say. The Session Manager finally is responsible to initialize the remainder of the registry. Remember, it's the bootloader, NTLoader, that opened and read in the system part of the registry, HQ Local Machine System. But, and that part of the registry was used not only by the bootloader, but also by the operating system to locate and load the system start drivers. But there are other major parts of the registry, like the software hive, the security hive, and the SAM hive. So it's at this point that those registry pieces are opened and initialized, which means a crash due to a corrupt registry hive at this point is going to result in no crash dump, because this is done before the paging file is open. And in the crash section we'll get to later, we'll see that crashes prior to the page file being opened are not recorded, because crashes are recorded in the paging file.
We haven't talked about the Windows subsystem being up and running yet, and this is the point where Session Manager starts to get that going. The windowing subsystem consists of 2 components: a kernel mode driver called Win32k.sys, even on 64-bit Windows ironically, that Session Manager loads and starts at this point. Win32k.sys implements the GDI part of Windows and the user part, so the graphical part and the windowing and Windows message part. The next step of Session Manager is to launch another user mode process, the second one on the system, CSRSS, which stands for Client Server Runtime Subsystem. CSRSS is the user mode part of the Windows subsystem. And now that that's up and running, we've got Windows API available for use by other processes. So the first Windows application that gets started is WinLogon, which is the interactive logon manager.
Now you'll have a visual cue that the windowing system was initialized, because that's when the system flips from the black startup screen, or in Windows 2000 the white screen, into GUI mode. The hourglass cursor appears. So if you see the system switch to GUI mode with the hourglass cursor, you know that you've got through the kernel initialization, Session Manager, and the initialization of the windowing system.
WinLogon takes over next, and its first job is to launch the Local Security Authority subsystem, lsas.exe. lsas.exe is responsible for local authentication to the machine. So whether somebody's logging on interactively through WinLogon or somebody's logging in through the network, through a file network share, LSAS is the one that ultimately makes the call as to whether they're allowed to connect to this machine. WinLogon also gets ready for accepting an interactive logon. It doesn't present the UI itself, though. It relies on a plugin called a GINA, or Graphical Identification and Authentication DLL. The built-in GINA in Windows is called msgina.dll, and it presents the UI that we're all familiar with that asks for your username, password, and domain. So this is when the logon dialog box would appear. WinLogon then starts the Service Control Manager, services.exe. Let's talk about that.
The Service Control Manager, or as it's affectionately known at Microsoft, the SCUM, SCM, is responsible to make one more pass through the system part of the registry, HQ Local Machine System Current Control Set Services, and look for services that are marked as a start type of 2. That was an automatic start service. This is mostly a set of user mode components, some of which run in their own process context, like the spooler service, some of which are DLLs that load inside to shared service hosting processes, like the svc host.exe that you'll see running on your system. However, there may be configured kernel mode drivers in your system marked as a start type of 2, automatic start. For example, CD-ROM burner software or even virus scanners have kernel mode drivers that are started by the Service Control Manager. So the Service Control Manager is not just necessarily starting processes, it may also be loading kernel mode drivers. This service startup, by the way, continues asynchronous to the ability to log on to the system. So while the logon prompt may have appeared, the Service Control Manager may still be initializing some of these automatic start services. One of the core mechanisms provided with Windows since Windows 2000 to repair and try to resolve boot start issues is the Recovery Console. It's a kind of a basic repair tool. It provides only a command line environment. It has a limited set of repair commands, but it is available on every Windows CD since Windows 2000. It's, I find, underutilized because if you're not aware of its presence, that you can boot off the CD, since that was not there present in Windows NT from the start, you might not have heard of it. Also, it can be used to repair installations other than Windows 2000 and later. For example, an NT4 disk could be accessed and repaired by the Recovery Console. The Recovery Console is actually built on a minimal Windows OS. So if you're booting the Windows XP CD-ROM, you're running a little mini Windows XP installation. If you're booting Windows Server 2003 CD-ROM, you're going to be running on top of the Windows 2003 server kernel.
Actually, the boot process that we just described that takes you all the way to Session Manager on the Recovery Console, the boot process goes to the same position, but the Session Manager image is the Recovery Console user interface that presents the environment that we'll see in a second.
Now, I've learned the hard way of the wisdom of installing the Recovery Console on your hard drive. I had a situation where I had a blue screen due to a bug in a driver, a video driver, I won't mention the manufacturer, and when I tried to reboot my laptop, the system wouldn't boot. In fact, the root directory of the C partition was corrupt, so it couldn't even find ntloader or boot.ini. I didn't have my Recovery Console installed locally, so I had to go find a Windows CD, which wasn't readily available to boot. Since then, I've always made it a practice to install the Recovery Console on the hard drive. And the way to do that is to run off the Windows installation CD WinNT32 with the switch/cmd cons. And that's something that's documented in the help file for WinNT32.
So let's pull up the Recovery Console and take a look at how it appears when you boot a system into it. And what we've done is we've got a Windows system here at the boot menu that ntloader's presented us. There's an entry in the boot.ini for the Recovery Console because we've already installed it locally under this hard disk, and I'm going to select it. And like we've said, this goes through virtually the same boot process that a normal Windows boot up would take. In a second, we're going to see the Recovery Console scan the hard disk looking for Windows installations, of which we have one. And it will ask us to select which one. And now in this case, there's only one. We've got to enter the number. This is something that's bitten me before, pressing enter and having the system spontaneously reboot. Recovery Console is now asking us for the local administrative password to the system. And it does this as a security precaution. Microsoft Enterprise customers feel uncomfortable with the fact that end users might be able to boot into the recovery console and then access the system unchecked. And so Microsoft's made the recovery console require that they enter the admin password so that only authorized users can get in and muck around with the system. If we type help, we can see that there's an extensive list of commands supported by the recovery console. For example, there's commands that you're familiar with in a Windows standard command line environment for deleting files, for doing directory listings, for copying files. There's also a number of other commands that are focused specifically on fixing broken Windows systems. For example, we'll see there's commands related to fixing the MBR or fixing the boot sector. There's also commands related to enabling and disabling drivers or services that might be causing problems.
We've seen that one of the limitations of the recovery console is the need to know the administrator password, and that's something that sometimes the user might forget or there may not be a record of. And so later we're going to see that Mark's ERD Commander, which is like a super recovery console on steroids, doesn't have that limitation. Also, for security reasons, the recovery console by default, unless system policies have been changed, limits the directories and the files that can be accessed by someone who's able to boot into the recovery console. We can see that if we go back to the recovery console, the default directory that we're set at right now is the installation we chose to repair, and I can do a directory, I can cd into other subfolders, I can cd to the root directory, do a directory, but if I try to cd into some other folder like the temp folder, I get access denied. And that's true of any folder except for the root, the Windows directory, and one special folder we're going to talk about later, system volume information, which is where Windows XP restore points are stored. The reason for this restriction is so that somebody who boots the recovery console would not have the ability to go and look at sensitive files that are protected by Windows permissions lists, because in the recovery console environment, the permissions lists are basically being bypassed here. Now, it is possible, using group policies and using the local security policy editor, to enable the ability to navigate to directories other than those three, the root, the Windows, and the system volume information directory. Mark, why don't you bring up that policy editor and let's take a look at the two setting changes that you can make that affect the recovery console.
Okay, I'm going to bring up the local security policy editor by going to the Start menu, going to Run, and typing secpol.msc, which is the MMC snap-in shortcut for the local security policy editor. Here under Security Settings, Local Policy, Security Options, you can find a lot of the group policy, local security policy settings. If we scroll down, there's a couple down here that are related to the recovery console. One is Allow Automatic Administrative Logon, and that's disabled by default. And the second, if I spread this open a little bit so we can see the full text, says Allow Floppy Copy and access to all drives and folders. Because another one of the restrictions is that you can copy data onto the system, but you can't copy it off. And again, this is to try to prevent people from taking sensitive information off the machine.
Now, one of the other limitations of the recovery console is there's no network environment. So there's no way to connect to other UNC shares. You can't edit files. There's no basic text editor. There's no registry editor other than the enable and disable commands, which go in and let you manually enable or disable services. It's also a command line environment, which is just frankly not as easy to use as the GUI environment that most of us are familiar with.
So I'm going to talk for a few minutes about ERD Commander, a tool that's part of the Winternals Administrator Pack. ERD Commander is a full-blown graphical environment that runs on top of a special version of Windows called Windows PE, or Pre-Installation Environment. Microsoft originally developed Windows PE with OEMs like Dell and Compaq in mind, so that they could create a factory floor imaging system that was built on top of Windows itself. People could write Windows applications to work as part of the imaging process. Traditionally, these OEMs used other environments like DOS as part of their imaging process, which makes laying down NTFS volumes, for example, a challenge. Winternals was the first ISV to license Windows PE, and we licensed it to build this recovery environment on top of it to give you a familiar Windows look and feel for your recovery operations. Now, I've booted this VM into ERD Commander. I'm going to go into full screen mode. And what we're looking at is the boot screen, or the logon screen, that ERD Commander presents after you've booted the system off of a CD containing ERD Commander. Like the recovery console, it scans the disk looking for Windows installations. It's identified one on this system. I'm going to go ahead and log into it, but you'll notice I haven't had to type in an administrative password to get access to that installation, a difference between ERD Commander and the recovery console. When we log in, ERD Commander displays a desktop that looks a lot like the Windows XP desktop. So you can see that there's a taskbar, there's a start menu, there's icon shortcuts on the desktop for My Computer and Network Neighborhood. And if we go open the start menu, we can start to see some of the advanced recovery and repair capabilities that ship with this product. For example, there's a command prompt. It's a little bit different than the standard command prompt in that it shows you the mapping of drive letters here in this environment, which might be different than when this system is booted normally. There's a private version or ERD Commander specific version of Notepad. There's file search. There's its own browser so that you can go to the web and troubleshoot problems by searching the Microsoft Knowledge Base, for example, or download drivers to the system to repair.
So the network is actually active at this point?
So the network is active at this point, and that's another key difference between this and the recovery console, is that networking is fully enabled. Not only that, if we go into networking tools, you can share the volumes of this system out to other systems. So for example, if you have a virus scanner that can work on remote file mapped drives, you would be able to do virus scans of this offline Windows installation through that facility. You can also map the drives of other systems on your network using the Map Drive wizard. And of course, you can change the TCP/IP configuration settings, which are by default configured to boot this thing for DHCP. If we go to the administrative tools, you'll see that there's a private version or ERD Commander specific version of the Sysinternals Auto Runs utility. There's a copy of the disk management tool that looks and feels a lot like the disk management tool that ships with Windows. And that is the point, is to make a recovery environment feel as comfortable and familiar as possible. So you can see, just like the standard Windows disk administrator, you can do things like format, delete partitions, create partitions. Here in computer management, which is mimics the standard computer management MMC Snap-in in Windows, you get system information, so you can look at attributes of the operating system that you're trying to repair, including what hotfixes it has installed. You get access to the event logs, so this is something you can check for to look for problems that might be related to the reason that the system's not booting. Like I mentioned, auto runs is in here, so you can look at the auto runs for different administrators or different users that have logged onto this machine. And it has a nice familiar interface for starting drivers and services or disabling and enabling them. Of course, you're not going to be manipulating the drivers or services of ERD Commander's environment, but that of the installation you're repairing. So the next time you boot that installation, these changes will take effect. It has its own registry editor, but this registry editor targets the registry of the offline installation. And if we go into System Tools, we're going to see a crash analyzer. So if your system's crashed, this tool you can use to have it automatically analyze the dump. Analyzing a crash dump is actually a relatively straightforward operation. We covered that on our crash analysis video. But this thing takes even the minimal work associated with that out of your hands and does it for you. Disk Commander is a tool that you can use to restore volumes that have become totally corrupted such that Windows doesn't even recognize their presence, or to undelete files on those volumes. So this will do optionally a low-level scan of your system looking for volumes that have been deleted and allow you to repair them and to copy data off of them. It's kind of a very advanced disk recovery tool. When you're ready to take a PC and repurpose it, maybe give it away, throw it away, or give it to another user, it's good to wipe the disk to get rid of any sensitive information that can be obtained. And the Disk Wipe applet here does a Department of Defense compliant 4-pass override of the disk, which the DoD considers sufficient for its own purposes in scrubbing a disk so that information can't be gleaned from people even using advanced electronic methods to try to get data off of the disk.
Mark, that makes me kind of wonder what kind of customers that you're selling that to.
Well, I think it's prudent in any corporate environment, if you're going to repurpose a machine, to wipe the disks first.
Okay.
If we go to System Tools, there's a File Restore utility, which is a lightweight file undeleter, so it's not able to tolerate corruption of volumes or missing volumes like Disk Commander is, but it provides a nice little search interface for looking for deleted files. And undeleting files, by the way, is something you should probably be performing in an offline environment. When you've deleted a file, and it's a file that you know that you've got a critical file you want to get the contents back for, shut down the machine as quickly as possible. Get into ERD Commander and use File Restore, because what you don't want to do is cause the file system or let applications continue to change the disk and possibly overwrite the sectors that contain the data that file used to occupy. Sometimes companies are afraid of applying service packs or hotfixes because they're not sure if their driver configuration that they've got on their systems is incompatible with the hotfix or service pack. If your system becomes unbootable because of such a change, the hotfix uninstall wizard lets you enumerate the hotfixes or service packs stored on the system and then undo them. So you can simply select them off, press next, and it will deinstall them. We talked about admin passwords. The Recovery Console requires one. ERD Commander doesn't require one to log on. ERD Commander goes one step further. Using the Locksmith wizard, you can change the local password of the password of any local account, including the local administrator account.
Mark, this is one that I know saved me personally. I had a Windows system in the office that I'd forgotten the admin password. I needed to do some maintenance, so I booted ERD Commander, ran the Locksmith wizard, and was able to safely reset the admin password. And I think safely is the key here, isn't it? Because there are tools on the internet that let you do this, but they're really risking the integrity of the security database.
Yeah, they actually reach into the registry hives and try to manipulate the data within this. ERD Commander uses a supported mechanism, believe it or not, to change the admin password. The next tool we'll mention is System Compare. If you've got a bunch of computers that are identically configured on your network and one of them is behaving erratically, you can use System Compare to compare the system state of this system with another one that should be the same. Very quickly lets you zoom in on changes that might be relevant to causing the problems. System File Repair. Windows keeps a backup of many core system files in what's called the DLL cache. System File Protection uses this backup cache. And the System File Repair tool relies on that background cache of information to go scan what system files are currently configured on the machine, will report any differences and let you replace those with backup files. So we're going to talk about dealing with system file corruption a little bit later, and what our recommendation, if you don't have ERD Commander, you can do these steps manually, but ERD Commander will automate it for you. And finally, System Restore. System Restore is a recovery facility built into Windows XP where the system takes snapshots of the system state periodically. And if you've got a system that's become unstable because you've installed a driver or an application, System Restore might not be available, at least the Windows System Restore, because to get access to the Windows System Restore, you either need to be able to boot normally or boot into safe mode. And if the driver that's causing the problem or the system corruption that's causing the problem is stopping the system from booting in those ways, ERD Commander can come to the rescue here, giving you an offline System Restore wizard so you can get access to those System Restores even if the computer you're trying to repair just won't boot into Windows under other circumstances.
So Mark, if people want more information about ERD Commander, where can they go?
www.winternals.com.
Let me just go there. Winternals.com. It's my second favorite website, SysInternals, of course, being the first. And here we see the homepage for Winternals. So,
and if you go down to System Tools,
okay,
and there's the Administrator's Pack. As we mentioned, ERD Commander is part of it. ERD Commander also comes in an emergency download version. So if you've got a problem and you need to have it fixed right away, you don't want to wait for the Administrator's Pack to be shipped for you, you can purchase a temporary version while you're waiting for the full admin pack to get to you so you can fix the problem and get up on your feet again.
Actually, I was a customer of the emergency download version myself and got a license key shipped to me, although Mark did give me a good discount. My
favorite recovery option in Windows is last known good. Why? Because last known good simply requires you to press a button and see if the problem will resolve itself. You get to last known good by pressing the F8 key during the boot process, which we saw earlier. So let's pull up the boot menu here in a VM. And you can see last known goods option is right here. Last known good configuration, your most recent settings that worked. Last known good is an option that doesn't work if your files have become corrupt. It only replaces the core system settings that the Windows uses to guide its boot process with the versions that were used last to boot your machine successfully. And we're going to see what the definition of boot successfully is in a little bit.
So when you choose last known good, what are you getting the last known good copy of? You're selecting a previously saved control set. A control set is a subset of the information in a subset of the registry. It's under HKey local machine system and what is on the running system current control set. It's the core startup information, the list of drivers to be loaded and core operating system settings. Let's take a look at this part of the registry by going to the registry editor, going to HKey local machine system, and here we see what looks like 3 control sets: control set 1, control set 2, and current control set. So there's actually 2. One of these is the current, and the other is the last known good. If we go to the select key underneath, still under HKey local machine system, we'll see on the right the definition of current and the definition of last known good. Current is 1 and last known good is 2. So the current control set is really control set 1 and the last known good control set is control set 2. So when you press the F8 boot option and choose last known good in this system, it would use the settings underneath control set 002 to boot the system. If you look at this display of the registry there on the left, you can see that the control set really is a subset of the registry. For example, booting from last known good will not help if the software hive has had corruptions or invalid data, or if the security hive or the SAM, the Security Account Manager database, has corruption. So booting from last known good relies not only on the registry system hive being intact and usable, but also the rest of the registry hives being available and intact as well.
The kind of scenarios where last known good will help you include the cases where you install a new driver and that new driver starts up early during the boot process and crashes the machine, or you change the configuration settings of an existing driver. For example, you open the control panel applet to modify driver settings or the video adapter settings, and you set them in such a way that triggers a bug in the driver and the system crashes during the boot or hangs during the boot. Also, if you go into the registry, that part of the registry where operating system configuration information is stored, we saw under Session Manager, there's actually a key under there called Memory Management where you can go in and tweak the parameters of the Memory Manager system in kernel mode. You can actually tweak those in such a way that the system becomes unbootable. And if you make a change to a location like that, simply going back to the last version of the control set that doesn't reflect those changes will get you out of that jam.
Now, some cases where last known good is not going to help is, first of all, if you've updated an existing driver that was loaded in the previous control set, then that driver is still going to be loaded if you boot from last known good. Also, if you have a driver that has a latent bug that all of a sudden has been activated, something else in the system has changed that's causing a problem in a driver to surface, booting from last known good is not going to help because that driver is still going to be loading. And as I mentioned also, if there are core system files, or in particular the registry files that are missing or corrupt, last known good is not going to help.
Another situation where last known good actually won't help is if the system has proceeded far enough into the boot that the system considers it a successful boot. And there's 2 things that have to happen for the system to consider the boot good and for it to make a copy of the current control set and label it as the last known good control set. 1, somebody's had to have logged into the system interactively, and 2nd, all of the automatic services have to have started up successfully. One of the cases that can bite people is if their automatic services aren't starting up successfully, because on professional systems, Windows is configured not to pop up the 1 or more drivers failed to start, 1 or more drivers or services failed to start dialog, which it does pop up by default on server systems. So client systems can actually be running and booting without ever getting a last known good.
So basically it's a good practice to check the event log on your client systems to make sure that all the services are starting successfully. Otherwise, you may not be getting a copy of the current control set that you could later select using last known good.
Now, if you pick last known good and it works, the system becomes bootable, that means that there's some data in the control set that was stopping Windows from booting successfully. And what you should probably do as a systems administrator to make sure that that problem doesn't occur on other machines, or to fully understand what caused that problem, you should compare the control set that failed with the one that got your machine booted successfully. When you choose last known good, it takes that control set that you're avoiding and labels it as the failed control set. On my machine, I've never actually had to use last known good, so if we go look at what it's got configured for the failed control set, it's 0, which is no control set. What you can do to find out what the difference is to export using regedit the failed control set and the current control set once you got the system booted to .reg files, load them into a text editor. I recommend avoiding Notepad, and doing a global search and replace of the part of the registry key names that are different. So you would want to change current control set to control 00N wherever N matches failed control set. Then use a simple file comparison utility or text comparison utility to see what the changes might be. There's going to be lots of innocuous changes or differences, but a quick scan through those and you should immediately be able to recognize those changes that aren't relevant versus those that might be significant with respect to a boot problem. The reason I say stay away from Notepad, by the way, is its global search and replace is a very inefficient algorithm, so it can literally take an hour for it to do a global search and replace of one of those .reg text files. The recovery mechanism to try if last known good isn't able to help is safe mode. Safe mode actually requires that you go in and diagnose the problem in most cases, but it's a version of Windows that might actually be able to boot successfully when the normal boot won't. It's actually a mechanism that was based on Windows 95. Windows 95 introduced this concept of safe mode, which is a version of the boot process that avoids non-essential drivers and services. Hopefully the problem that's causing, or the driver or service that's causing your boot problem is one of those third-party drivers or services or one of those non-essential components that Windows avoids when it's booting into safe mode. However, safe mode does require that those core components that are involved in the safe mode boot be consistent and non-corrupt.
So in order to activate safe mode, you go to, you press F8 during the boot process. NT Loader stops the boot process and lets you select the various options from the special boot options menu. Let's switch over to our virtual machine and take a look at that menu again, and we can see that the first three options relate to safe mode. The first one, safe mode, boots Windows without any networking environment in a GUI mode. So if you log in, or when you sign in, Explorer will come up. You'll have access to the full Explorer GUI environment. Safe mode with networking also starts the GUI environment but loads the Windows networking component. So the default safe mode, the network is not up. The third option is safe mode with command prompt. And the only difference is that the logon process will run the command prompt instead of explorer.exe. The windowing system is still started, so you're actually still booting a good part of Windows. The whole windowing system is initialized. From that command prompt, for example, you could run Explorer, you could run other GUI applications. It's just that CMD is run instead of explorer.exe. And we'll see that when we look into the internals of safe mode next.
Windows is actually not hard-coded to define what safe mode is. It's guided by registry values. Specifically, a location under HKeyLocal machine. I'm going to pull up the registry editor here. HKeyLocal machine, system, current control set, control, safe boot. You'll see that there's two keys under that main key, one minimal and the other one network. The minimal key guides safe boot with command prompt or safe mode with command prompt, and network guides safe mode with networking. And minimal, by the way, also guides normal safe mode. If we open up one of those keys and look at what's underneath them, we see something that looks very similar to what we saw under the services subkey, where drivers and services are registered. The way that safe mode processes this is the I/O system, for example, early in the boot, when it's going to load boot start drivers or system start drivers, checks to see if that driver is listed by its group value or explicitly by name here in the appropriate safe boot key. Only if it's present there will it actually start the driver. The same thing applies to the Service Control Manager later in the boot process, which looks in here to see if it should start the service. If we look in the network node, It has all the same contents as Minimal, except it has networking drivers like AFD, which is the Windows kernel mode sockets driver. What distinguishes safe mode from safe mode with command prompt is the value here, alternate shell. And you can see the default here is command prompt. So instead of running Explorer, you boot with safe mode with command prompt, and it will actually load whatever program's listed there. So you could replace that with something else, for example.
In fact, in one of our labs, we just for fun changed that to sol.exe. We boot, press F8, choose safe mode with command prompt, and up comes Solitaire.
Now, I have to mention that there's one exception to the way that safe mode processes drivers. And the I.O. system automatically ignores safe mode, these safe mode keys when it's going to load boot start drivers. The thought behind that is that if it's marked as a boot start driver, it's necessary for it to start for the system to even boot in the first place. And omitting it, you'd be left with an unbootable system. So it's going to not even look to see if the driver's referenced in these keys. It's simply going to start it.
I've had a couple of cases, Mark, where some friends had their systems infected with spyware, and they had to boot in safe mode actually to remove the auto start locations. They were able to run your auto runs tool to disinfect or remove some of the malware that was starting. What's a scary thought is that malicious software could actually modify the safe boot key and configure itself to be loaded in the minimal or network set.
Right. Well, all it has to do is if it's a driver component, which we're seeing a lot of rootkits now configure themselves as drivers or have kernel mode rootkits, they configure themselves now as boot start drivers specifically so that you can't get rid of them by booting into safe mode. And you need to do an offline clean from an environment like the recovery console or ERD commander.
So basically safe mode may not be that safe anymore.
That's at least not when it comes to malware.
Now, once you start safe mode, whether you chose safe mode with command prompt, with networking, or just the regular default safe mode, if it's a Windows XP system and you had System Restore enabled, a message box will appear asking you, would you like to enter safe mode, or would you like to invoke System Restore? And invoking System Restore may be the quickest way to get your system back to a working condition, because System Restore will undo, as we're going to explain later, changes made to various registry hives, including user profiles, files that have been replaced that may be affecting applications. Proper functioning will be restored. So that's one option if you're using System Restore, just to go ahead and press No, bring up the System Restore dialog, pick a date in the past that you knew that the system was working properly, and let Windows go ahead and roll your system back to a known working point. On the other hand, if you've made a number of changes that you don't want to roll back, you need to perform some manual analysis, then press Yes, and you're going to then basically sign in. Explorer is going to come up, or the command prompt if you chose safe mode with command prompt. System Restore was introduced in Windows XP to provide an easy way to undo a set of changes to the system that may have involved files other than the core Windows operating system files. For example, third-party applications or third-party DLLs. One of the things that System Restore is good for is being able to quickly and easily pick a point in time in the past where you knew the system was working properly and roll that system state back. System Restore, however, requires that the basic system files be bootable. So if you have a completely unbootable system, then you're not going to be able to start Windows XP in safe mode to do a System Restore. Now that's one of the things that your ERD Commander, Mark, provides access to. So if you have an unbootable system, you can boot ERD Commander from WinTernals and choose its System Restore wizard to roll back to a known good point. System Restore is not included with Windows Server systems, and on XP it is enabled by default. You can find the configuration for System Restore if you go to the Start menu, right-click on My Computer, go to Properties, and you'll see the System Restore tab. And Mark, you have the default, which is that System Restore is not turned off, so there's a checkbox to disable it. One of the settings you can set on System Restore, if we click on the Settings button, is how much disk space can be assigned for System Restore points, because each time a restore point is taken, there's a certain amount of disk space used, and then as files are replaced, Windows has to keep the original version so that it can perform a rollback. So if we zoom in on this, it looks like you've allowed, Mark, 12% of the volume, which I believe is the default maximum, so about 3.5 gigs of your main C drive, C volume. Restore points are created by default every 24 hours. They're also created on some software installs, depending on the software installation mechanism that you use. For example, the Microsoft Software Installer will automatically take a restore point. so that if you've installed the software program and it's caused other applications to fail, you'll be able to roll back to what the system was like before you installed that application. Another trigger for taking a restore point is installing an unsigned driver. Or you might explicitly request a restore point yourself. If you're about to make some changes to files or settings in the registry, you might want to take a restore point so you could go back to that known good point. And you can do that by invoking the System Restore Wizard, which is accessed through the Start button, Help, bringing up the standard Windows XP Help and Support. So I'm clicking on Help and Support, and right on the main page there's an option that says Undo Changes to Your Computer with System Restore. Again, that's available on XP client systems, not on servers. So I'm clicking that option, and this brings up the System Restore Wizard, and I basically got two choices. I can do a restore to an earlier time, or I can create a restore point. So here's how I would if I wanted to take a manual snapshot at a point that I'm about to make some setting changes. Now let's go ahead and choose Restore My Computer to an earlier time, and don't worry, Mark, I won't actually do a rollback. If I click Next, now we can see a little calendar that shows by the days highlighted in bold the dates that there were restore points. So for example, if we look at yesterday on the 19th, there was a restore point because, Mark, you installed the Windows support tools. If we go back to the 18th, you must have had some software updates, Windows XP hotfixes, I believe. Same with the 16th and the 14th. You installed the debugging tools. You installed, I can see the latest version of the Microsoft anti-spyware. So it looks like, Mark, you're taking pretty good care of your laptop. Good job, Mark.
So when you take a system restore point, Windows automatically snapshots a number of databases, including the registry hives, the ComPlus registration database, and user profiles. It also makes copies of certain files not protected by Windows File Protection, and then it starts monitoring a number of file extensions across all the volumes on your system. Specifically, 569 file types are monitored, and when System Restore sees a change about to take place to a file with one of these extensions, it makes a backup copy that it can later restore to. The list is actually documented in the Platform SDK, and it includes things like .exe and .ocx and .sys, .dll, files that you would think of when you think of system files. It explicitly ignores or omits the extensions that are associated with data type files like .text and .doc, .ppt, because what you don't want to have happen is when you are rolling back your system to fix a system reliability problem, you don't want your data to get lost in the process. And so those file types are excluded from that list.
So when System Restore is active, System Restore, when one of these registered known file types is changed, replaced, or deleted, a copy is made of the original version in the Restore Point folder representing the current snapshot of the system. And this is a folder a couple levels deep underneath a hidden system folder called System Volume Information. That's a folder that if you bring up Windows Explorer, I'm going to bring up the Explorer dialog now, and I look in the root of the C drive, there is a folder called System Volume Information. Interestingly enough, Explorer says folder is empty, and that's because if I try to click on it, I get access denied. This is a folder that administrators don't even have access to, Mark. So it's something that is meant just for the operating system to access. However, we're able to navigate into that folder using your psexec tool because psexec allows me to start a command prompt running under the system account. And it's the built-in system account, the local system account, that does have access to that folder. So I'm going to do a psexec -s, which means run the command under the system account, cmd.exe. I've now started a command prompt running under the system account, and if I go to the root directory, I now can cd into system volume information and do a dir. Now, no files show up because the files are hidden and system, so I do a dir/a:/h, and now I see a subfolder beginning with _restore. I'm going to cd to _rest**, and now do a dir, and here we see the restore points dating back some months that were taken over the course of the life of this laptop. The most recent restore point, RP92, cd RP92, is the restore point that was created when you last installed those Windows support tools. So if I do a directory of this folder, these files that begin with A represent files that match the special file type list that you referred to. For example, here's a .sys file that you must have replaced or deleted, an MSI file, some links, some shortcuts. So these are, again, files that are considered protected that this is a copy of. The names have been changed The original file names are in a database. And if I were to roll back to the previous restore point, here's the original versions that the System Restore wizard can then take and put back onto the system.
And if you go into the snapshot directory, Dave, that's where you'll find the backup copies of those various database files, including the registry hubs there.
This is a very important point because every time a restore point is taken, Windows makes a copy of the core Windows operating system registry hives, the Security Account Manager database, Security database, Software, and System Hive, in addition to all of the user profiles defined on the system. So we're going to see later, for troubleshooting, this is the best place to go in the recovery console if you're looking for an up-to-date registry hive to replace if, on the rare case, you've experienced hard registry corruptions.
System Restore is implemented as both a service and a driver. The service responds to your request to create System Restore points and then tells the driver to create a System Restore point directory. The service snapshots the various databases into that directory, and the driver starts monitoring for changes to files. It's a type of driver called a file system filter driver. File system filter drivers can see all changes to any file or directory as they take place because they layer themselves above the file system drivers that come on the system, like NTFS. If you've got an on-access virus scanner, for example, it is also implemented as a file system filter driver, which stops file opens in their tracks, scans the file for a virus, and only if the file is clean does it let the open through to the underlying file system. FileMon is another example. And the System Restore filter driver simply looks to see if the file that's about to be modified matches the special criteria, including the file extension, sees if it's already made a backup of that file in the System Restore point directory, and if it hasn't, then makes a backup of the copy of the file before it lets the modification proceed into the file system driver. When you choose to roll back, it's at that point the System Restore wizard then will reach into the restore point directories, copy the files back out to their original locations, restore the registry hives, and you're always forced to reboot in order to apply those changes and make them active.
Now, beyond just using System Restore for its native capabilities to roll the system state back to a known good point, we mentioned System Restore is invaluable when it comes to dealing with systems that won't boot due to registry corruptions. And it's in that restore point subfolder you'll find a copy of the registry hives at the point that the restore point was taken. You'll need to use some kind of offline tool like ERD Commander or the recovery console to go replace that file, and we're going to talk about how to do that in the registry corruption section.
Let's take a look at a couple of problems that might be preventing your system from booting, their associated symptoms, and how you'd fix these kinds of problems, starting with master boot record corruption. This type of problem can manifest itself in different ways depending on how corrupt the master boot record has become. For example, you reboot the machine, you see the black screen that comes after the BIOS post message, and the system hangs. Or you see a white text message appear on the screen that says invalid partition table, error loading operating system, or missing operating system. The cause of this could be master boot record corruption.
So if you're suspecting that the master boot record may be corrupt, you can boot the recovery console and use the fix MBR command. I'm going to go bring up the virtual machine running the recovery console here. We've already booted into it, and I'm going to go ahead and type fix MBR, and it's giving me a caution. Do I want to rewrite the MBR? This is coming because likely this is a virtual machine. Let's go ahead and write the master boot record. It's now been written, and now when I exited the recovery console, it would reboot, and hopefully that would fix the boot problem.
There's actually a limitation to that command, though, that you should be aware of, and that's that it only rewrites the code portion of the master boot record. The partition table it leaves alone. So if the corruption is extensive enough to corrupt the partition table area in the master boot record, that command won't fix the problem. And what you need is a third-party disk fixing utility, like Disk Commander inside of ERD Commander, which knows how to go and rewrite master boot records, including the rebuilding of those partition tables. Another problem that can manifest itself in some ways similarly to master boot record corruption is corruption of boot sector, the first sector on the system volume that the master boot record actually reads in and tries to execute. Symptoms here can include the black screen, again, that would come up after the BIOS post where the system hangs, or a message on the black screen like a disk read error has occurred, NT loader's missing, or NT loader's compressed. The cause might be boot sector corruption, and the solutions in this case include, similarly to what Dave just showed you, booting the recovery console and executing the fix boot command. The fix boot command actually is much more reliable than the fix MBR command because it knows how to completely restore the boot sector of the volume.
Shall I try and fix the boot sector on this virtual machine?
Let's go ahead and fix it.
All right, I'm typing
just
fix
in case
boot.
there's something wrong with it.
Are you sure you want to write a new boot sector?
I'm not sure, but
we'll go ahead and try it. And notice it says the file system on the startup petition is NTFS. That's relevant because the boot sector code, as we described in the boot process, has to be able to interpret the file system on that volume you're booting from. So that's a primitive NTFS file system that is able to then locate the root directory and read in the bootloader.
There's one thing I also like to point out. Whenever you have a boot problem and you're going to boot in the recovery console, it's always a good thing, or just a safe thing, to check disk the volumes first, because the problem might manifest itself as a symptom that you connect with another type of problem when it's actually corruption of the disk or corruption of some file, like NTLoader, for example. We saw some messages that could show up as causes of or as the result of boot sector corruption that might actually be the result of NTLoader corruption. So it's always the best practice to boot in the recovery console, run a check disk first.
And by the way, that saved me the night before a presentation. It was a Sunday night in Norway, actually. I had tried to boot my laptop. This was also after a blue screen from a video driver, and wasn't able to boot. This time I did have the Windows CD with me. I had not installed the recovery console on the hard drive. I hadn't learned that lesson yet. Booted the recovery console, typed check disk, rebooted, the system was up and worked fine. So it really does work. Another phase in the boot process where a file could prevent the successful boot of the system is if the boot.ini file is corrupt. Boot.ini is a text file that, as we discussed in the boot process section earlier, lists the various Windows system volumes and the directories where Windows operating system files are located, along with various switches that may affect the load and startup of the system. If boot.ini is somehow corrupt, you may get boot devices inaccessible, or ntoskrnl.exe missing or couldn't be located. Now in Windows XP and later, the NT bootloader is smart enough, if boot.ini is missing or corrupt, to actually by default go look for a directory called Windows on the volume you're booting from, and in most cases that's going to work. But in earlier versions of Windows, if boot.ini was missing or somehow malformed, the system boot would be halted at that point. Some of the causes for this could be the file, as I mentioned, being missing, somehow corrupted, or out of date. For example, because boot.ini refers to partition numbers on the volumes you're booting from, the disk you're booting from, if the disk configuration changed, you made some hardware configuration changes, references to partition and hardware disk numbers may have changed such that it's not able to locate the Windows installation. So the solution would be boot into the recovery console and perhaps first do a check disk, which Mark mentioned earlier, reboot. If that doesn't work, you can use the bootcfg/rebuild command. Let's go take a look at what that command does. So we're going back to the virtual machine running the recovery console, and I'm going to type bootcfg/rebuild. It says it's scanning all the disks for Windows installations. And now it's completed its scan, and we can see that it found one Windows installation, C:\Windows, and it asked me if I'd like to add that installation to the boot list. So this is going to be rebuilding my boot.ini from scratch. I'll say yes. It gives me a load identifier. I could give it a name, for example, Windows XP. And then I could, here at this point, add some of the load options, like debugging mode or some of the other switches you can pass to boot.ini. I'm going to press enter. And now I'm going to type boot.ini. And this is the boot.ini that's been modified. If you notice, it added, if you look at the line that says Windows XP, I'm circling it now. That's the line that was added by the bootcfg. It didn't replace the file, it added another boot entry to the existing boot.ini.
The next class of problem we'll look at is your system registry hive has become corrupt. And this hive is, or another registry hive has become corrupt, like your software hive. These hives are critical to the operation of Windows. Even hives other than the system hive, like the software hives or even user profile hives that are loaded later, can cause the system to not boot successfully. One of the symptoms that could be exhibited by a corrupt registry hive is that you get a blue screen during the boot process, and if you've got the default configuration for how the system responds to a crash, you might not even see the blue screen because the default configuration has the system automatically reboot, and if you don't have the system configured to take a kernel mode or full system crash, the reboot is so fast that unless you're sitting there watching the screen intently, you could miss it.
So in that case, you're going to be kind of in an endless reboot scenario because it's going to reboot, crash, reboot, and crash, reboot, and crash.
Right. And some of the causes of corrupt registry hive are the disk itself is corrupt. So it's not the internal data within the hive that's become corrupt, although data can become corrupt in the hive. If you, for instance, have a driver that's running in corrupt memory in the kernel before it goes out to the registry hives, that could, of course, cause your registry hives to become corrupt.
So the solution to this kind of problem is to boot the recovery console and again first run a check disk because that might repair the volume sufficiently to be able to access the registry hives. If the system still fails to boot, at this point you will need to go locate a good copy of the corrupted or inaccessible registry hive. And there's basically three choices or three places you should go. The first place you should go, if it's available, is the most recent system restore point folder. That's only going to be available on Windows XP systems. And again, only if that's been enabled. It is enabled by default, although some systems administrators turn it off. If that's not available, then you can go to a recent system backup, get the file, and using the recovery console, restore that file. And the last choice is the Windows repair folder. The reason the Windows repair folder is the last choice is that's a copy of the registry hives that were made when you initially installed Windows. And I learned the hard way the importance of updating the registry hives in that folder. I had a Windows 2000 system, so there was no system restore point folder. I had done no backups, so I had to go to my Windows repair folder to get a software hive. My software hive had been corrupt. And while it did allow me to reboot my system, which was a good thing, I had to basically reinstall all my applications and make all my application setting changes again. It is possible to update the copy of the registry hives in the Windows repair folder. And on Windows XP and later, you can do that with the NT backup tool. Actually, Windows 2000 and later, the built-in backup tool has an option to, on Windows 2000, explicitly update or back up the registry. On Windows XP, if you choose a system state backup, which is one of the options in the Windows backup, one of the first things it does is update the copy of the registry hives in the Windows repair backup subfolder. So that's a good practice. Once you've set up your system, fire up Windows XP backup, do a system state backup just to get a fresh snapshot of the system registry hives in that Windows repair backup subfolder.
Let's take a look at how you would get those backup system restore hives and replace the hive locations that Windows references as it boots. The first step would be, of course, to boot into the recovery console. Then what you have to do is cd into the location where system restore places those backup registry hives. I'm going to navigate into that directory on a live system by using psexec to launch a command prompt in the local system account, because by default the system volume information directory under which system restore points are stored is inaccessible to any account other than the local system account. The psexec command comes from sysinternals, and the -s switch says to run the specified command under the local system account. So now I have a command prompt running as local system. I'm going to cd up to system star, which is enough to match the system volume information directory, do a dir/ah, and underneath I can see the system restore subdirectory, which begins with _restore. So I'm going to type cd res star. Now I'm in the restore point directory. You're going to want to navigate, of course, into the most recent one, which is going to be the one with the highest index number, in this case 92. Do a dir in there, and there's a snapshot subdirectory where this registry hives are stored. So now I'm going to cd into the snapshot directory. If we do a dir, here are the system hives. For example, we can see their registry machine system, which is the backup version of the system hive as it existed at the time of that restore point. So the goal now is to get one of these hives, the SAM hive, security, software, or system hive, depending on which one we believe is corrupt, to the location in Windows where it will reference it the next time the system boots. And that location is under the Windows System32 config directory. If I do a dir in here, we can see the actual live system hive. Now I can't replace that hive in a live Windows system because that file's in use, but if we were in the recovery console, I'd be able to copy a registry machine system backup file over to this directory and rename it system. and try rebooting the machine and seeing if the problem had corrected itself.
You know, this actually worked for my dad, who had an unbootable system. The software hive was corrupt. He had a blue screen. He called me up, and he was able to see the blue screen that read to me that the software hive was corrupt. So over the phone, I had him boot the recovery console and painfully CD into the system volume information folder. There's no shortcuts or wildcards. Read out to me the restore point folder name, CD there, found the most recent restore point, went to the subs folder snapshot, executed that copy command, and rebooted the system, and everything worked. That was a satisfying mark. Now, if System Restore is not available and you have hard registry corruptions, again, boot the recovery console. You're going to have to fall back to a potentially old copy of the registry hives that were put in the Windows repair folder when the system was originally set up. Let's go take a look, Mark, on your system. I'm going to navigate to your C Windows repair folder, and let's take a look at the date of the files. And it looks like June 2005. Mark, doesn't look like you've done any kind of update of your registry hives.
You're right. I better go do a system state backup.
Actually, you're okay with this one because you have System Restore on, but were this a Windows 2000 system, doing a backup of the registry would be helpful. And that was another case that happened on a laptop of mine. I had a software hive corruption due to a bug in a driver. This was a little complicated though, Mark, because this laptop had no bootable optical drive. So I couldn't boot the recovery console to replace the software hive back in the Windows System32 config folder. And I have to say, once again, one of your tools saved my hide, and that was NTFS DOS Professional. I did have a floppy on this older laptop, but no CD-ROM. It was an ultralight with no optical drive. So I booted a DOS floppy, which I hadn't done in a while, loaded NTFS DOS Professional, which Mark graciously gave me a free license for, and I was able to CD right to the Windows repair folder and copy the software file into Windows System32 config, and my laptop was booting. So thanks, Mark. I appreciate it. If the boot process has gotten to the point where the bootloader is loaded, it's able to load and process the system hive, and then goes to load some of the core system files and they're corrupt, this may cause a problem in the boot process. You may see this as an error message from NTLoader that one of the core operating system files like NTOS kernel.exe, hal.dll, or other files are missing or corrupt. You could also have a blue screen with a reference to a corrupt file. For example, if kernel32.dll is corrupt, that's going to be a blue screen later in the boot process. The causes for system file corruption could be actual disk corruption, or the file is actually missing, or an individual file has been corrupted.
So the first step in troubleshooting this kind of problem, of course, is to boot in the recovery console and run a check disk. Hopefully it's just disk corruption and it's able to repair itself so that you boot the machine and get up and running again. However, if check disk reports no errors, then you probably do have corruption to one or more system files. So the goal here is to get a backup replacement for the identical system file. Fortunately, Windows keeps backups of many of the core system files in a directory under Windows System32 called DLL cache. Let's navigate into that directory on my system here. I'm going to open up a command prompt and navigate to System32 DLL cache. And you can see that there's a whole lot of directories, files in there. For example, kernel32.dll, one of the core Windows system DLLs. There's a backup version right there. So if that file identified as being one that was corrupt, I could simply copy that out to the original location, which is under the parent folder, System32. However, if you end up repairing one executable or one DLL, try rebooting the machine and get the same kind of error that indicates that the system has still has more corrupted files, then what you need to do is go find more replacements or be able to replace entire batches of files. And one way you can do this is to go to another system and that's identically configured and simply copy the files from that system onto your local system. Say copy them to some kind of media like an optical disk, and then get into the recovery console or another offline environment, copy those files over. If you can't find another system that has files that are of the same hotfix and service patch level, last kind of fallback step before you fall back on reinstalling altogether is to do a setup repair install. When you do a setup repair install, which is one of the options you get when you boot off the Windows Setup CD, Windows will pull the files off of the setup CD for all the system files and replace those that are on the live system. And the reason that I say that this is a last fallback and one you should approach with some caution is that the Windows registry is not affected. And so the Windows registry might believe that you've got several hotfixes or service packs installed where the files that come off of the setup CD don't reflect those more recent updates. And so now you've got kind of a system that's in a weird state where it believes it's got hotfixes and service packs installed, but you've actually lost them in the process of the setup, repair, install. The next class of problems we'll look at are those that occur later in the boot process than the ones we've just discussed. For example, a hang that happens after you log in, or a crash that happens right after the splash screen occurs. And again, want to emphasize that if your system's configured in the default configuration and you're running Windows XP or higher, it's set to automatically reboot in the face of a crash. And so you might not be aware that your system's out on your network or even rebooting after crashes, because an end user might not even be seeing the crashes, and these machines can end up caught in an infinite reboot cycle. Some of the causes that we'll see that are responsible for symptoms like this include buggy drivers, hardware problems, or bugs in Windows itself.
Now, if you're getting a crash or a hang during the boot, your first step would be to choose last known good. So reboot the system, press F8, get the special boot options menu, and try booting from the last known good control set. And perhaps that will, by using a previously known good copy of the system settings, be able to boot the system successfully. However, if that still fails, then try booting in safe mode. If the system boots in safe mode, you're still faced with the problem determining why safe mode worked when booting normally did not. And that's going to require some investigation that we covered in the safe mode section. If you can determine the faulty driver, which might mean analyzing a crash dump or looking at the drivers that are not configured to load in safe mode, you may be able to repair that driver, update it, replace it, or try rolling the system back to the previous known good restore point if you have Windows XP with System Restore enabled. Finally, if safe mode still fails to boot the system, it crashes or hangs on boot, then you're going to need to boot the recovery console or perhaps Mark's ERD commander for some manual offline repair.
Safe mode works where normal boot might not work because it relies on just a core set of drivers or services to get the system up and running. Hopefully the problem lies in one of those third-party or add-on drivers or services that Windows doesn't consider essential. If the system was crashing, what you should do at this point is go find the crash dump file or configure the system to generate a crash dump file and reboot the machine and generate one that you can get to from safe mode. Copy that crash dump file off the machine or even analyze it right there from within the safe mode environment, assuming you've booted with networking so that you can access symbols that are related to the files on that system from Microsoft Symbol Server.
If you're able to determine the driver that's causing the problem, you can try to roll back the driver to a previous version if you have Windows XP. And Mark's going to explain in a moment how the driver rollback feature works. If there's no backup copy available or it's an early version of Windows, then try disabling the driver. And you can do that in safe mode by bringing up the registry editor, manually disabling the service, or perhaps in the hardware device manager. My Computer Properties, go to the hardware tab and click Device Manager. For a non-plug-and-play driver, you can disable devices from there.
So if you can determine what driver is causing the system to fail during the boot, either through it being obvious because you've just installed some new device, then the driver associated with it is the one causing the problem, or you're able to analyze the crash dump and identify the buggy driver, the next step is to repair that driver or fix the problem. And there's a couple of options usually to do this. One, if it's a driver that you've recently updated and that update now is the problem, you can, in Windows XP and higher, roll back to a previous version of that driver. Otherwise, you need to either update the driver with a new version or disable it altogether.
Driver rollback, recovery feature added in Windows XP, causes the I/O system to keep a backup copy of drivers that have been updated that were previously installed in the Windows System 32 Reinstall Backups folder. Let's bring up the command prompt and navigate to that folder. We're in Windows System 32. We're going to CD down to the Reinstall Backups folder and do a directory. And here we see subfolders that contain updated drivers at various points in time. We'll go to the most recent one, go to the drivers file subfolder, and here are a set of drivers that were updated that we could roll back. Now the way to activate the driver rollback is to go to My Computer, Properties, go to the Hardware tab, click on Device Manager, choose the device that you'd like to roll back. Let's take, for example, your sound device. We'll pick, one of the network drivers. Right-click Properties on the device and go to the Driver tab, and you'll see the Rollback Driver button. And as the text says on the bottom, if the device fails after updating the driver, roll back to the previous version. This is something you can perform in safe mode. So if the system is not booting because the updated driver is causing the crash or a hang, boot in safe mode and roll back to a previously known good copy of the driver.
Now, if you don't have a previous version, it's a driver that you just installed or hasn't changed since you first installed it and you've gotten through several reboots so that there's no backup version of it to roll back to, your alternative then is to go check the vendor site for an update. If there is none and you've determined that this driver does have a bug in it and your system can run okay without it, the next step is to disable the driver altogether. And you do that from the same place, the device manager that Dave was just showing you. I'm going to pull up the device manager again and double click on, or take a look at the properties for that same network driver, and you can see on the General tab it says device usage down here at the bottom. Use this device or enable. That turns into a drop down where the other choice is to disable the device, and so that's what you want to pick. Now, certain types of device drivers don't show up in this list because this device manager by default will only show you plug-and-play related or hardware-related device drivers. To see those other types of drivers that aren't related to plug-and-play devices that could still be responsible for problems during the boot process, go to the View menu and select Show Hidden Devices. And what you get is a new node there that appears called None Plug-and-Play Drivers. Open up that node and you'll see the entries for device drivers that don't have any associated physical hardware. For example, the Windows Mount Manager. And when you open the properties for that, you still get the ability to enable or disable those devices or those drivers. If you're talking about rootkit-based malware that installs itself as a driver that you want to disable, those will almost always show up in this part of the device manager.
If you can't determine the faulty driver, so you're getting crashes that don't have a repeatable pattern or porting off as the culprit being Windows core system files, system drivers, then you want to try enabling Driver Verifier. Driver Verifier was a tool added in Windows 2000. It's present on all Windows systems, client and server, since Windows 2000. And it permits you to enable some rigorous checking such that if a driver performs an illegal operation, it will be caught more likely at the point it performs that legal operation so that the crash more directly points at the culprit. If Driver Verifier doesn't produce a useful crash, then you may be left with booting the system in safe mode and try disabling drivers that you don't need so that you arrive finally at a system that boots. So disable drivers that aren't being loaded in the safe mode subset one by one. Go boot normally. If the system boots, then you've now isolated the driver. And really, as a last resort, system restore, because system restore means you're going to undo changes and software installations that you'll have to go repeat.
In some circumstances, safe mode might fail the same way that normal boot does, and that would occur if safe mode includes the same problematic driver that the normal boot does. Safe mode, for example, will automatically load all boot start drivers, those drivers that are considered essential to the system even getting up and running. And if a problem occurs in one of those drivers, safe mode is also going to fail. Malware, for example, rootkit kernel mode based malware oftentimes now marks itself as a boot start driver specifically so that it can also interfere with the operation of safe mode and prevent you from cleaning the malware from safe mode.
So if you're having a situation like this, you could boot into the recovery console and look at the last line of a file that you can generate using the special boot options menu called a Windows boot log. Windows boot logging is an option, which we saw earlier on the special boot options menu, that causes the system when it's booting to record a list of all the drivers loaded in a file called ntbootlog.txt in the Windows directory. So if you enable boot logging, boot the system normally, it's going to crash or hang, then reboot the system in safe mode, reboot in the recovery console, look at the boot log text file that was generated and try to determine what the last driver loaded was, or perhaps inspect that file for a list of the drivers being loaded, and maybe you're going to see one, something malicious or suspicious that shouldn't be there. If you find the driver that's loading that you suspect is causing the problem, you can disable it from the recovery console with the disable command.
So final alternative to troubleshooting crash that's occurring in normal boot and safe mode is to connect to that machine with a kernel debugger so that you can connect with that machine and look at the state of it at the time of the crash. Because crashes that happen early in the boot process won't generate crash dumps, even if you've configured them to do so. And one of the ways that you can configure the target system, the one that's exhibiting the problem, to boot in a way that causes the kernel debugger part of the kernel to activate and wait for a connection from another machine is to boot it into into debugging mode, which you can get to through that special F8 boot menu. If we go back to our VM that's ready, sitting there at the boot menu, you can see debugging mode down here. Now this is not the preferred way of booting a machine into kernel debugging, because debugging mode here chooses default conservative boot options or debugging options. For example, it chooses the serial port on the system, serial port 2, and it chooses a very low baud rate, 19200, which is painfully slow to debug over. So what we recommend instead is that you get into the recovery console, for example, edit boot.ini, and add an entry into the boot.ini that adds the debug parameters that enable faster debugging. For example, specifies that you debug over IEEE FireWire if the system supports FireWire and you're running Windows XP or later. At the minimum, specify serial port and the maximum supported baud rate, which is 115/200, which is significantly faster than the default. At the time of the crash, you'll be able to access the machine and then take a look around to see what the cause might be.
So if you've booted the target system in debugging mode, whether you chose to just press F8 and choose the defaults, or you configured the boot.ini in the target machine to use one of the more advanced options or a faster baud rate, you're going to then bring a host computer, perhaps a laptop with the Windows debugging tools installed, connect it to the target computer using the appropriate interconnect, serial no modem cable or FireWire for using it. In Windows Vista, USB 2.0 is going to be supported. And you're going to start the debugger and choose in the WinDebug menu the option to connect to the target, specifying the proper connection. And let's go take a look at that option. We're going to go to the Start menu, All Programs, Debugging Tools for Windows, WinDBG. And on the File menu, the option to connect to a remote kernel debugger is File Kernel Debug. And you can see there's several tabs. The default tab is using a serial COM port. Then we have FireWire, USB 2.0. So, for example, if I pick the COM1 on this system, we can see the debugger then is now waiting to connect. If the system had crashed and we were connecting to an already crashed system that was booted in debugging mode, the connection would occur and we would see actually the bug check code, the reason for the crash displayed. If we were trying to connect to a system that was hung, we would have to at this point click debug break, which would send the appropriate commands over the interconnect to break into the kernel debugger on the target system and allow us to then go inspect and see what was going on at the time of the crash or the hang. Once you've connected WinDBG to the target, you can use WinDBG's built-in crash dump analysis command, bang analyze -v. WinDBG will present to you the reason for the crash and the potential culprit. And it will say probably caused by and give a driver name. And it may or may not be that driver. There's some other advanced techniques that we cover in our crash dump analysis video that will help you to take the output from WinDBG, interpret it, and decide whether you need to take further steps like enabling driver verifier to try to get a better crash. If at this point you're not able to solve the crash, but you'd like to make a copy of the crash so that somebody else could work on it, you can make a copy of the system's state by using the .dump command to save the dump file for later analysis on the host machine. Keep in mind that that's going to be a slow operation if you're doing a full memory dump copy over a serial cable. You could choose, for example, very quickly to make a mini dump. .dump/m makes a mini dump, and that's going to be a quick operation even using the slow baud rate default settings. So we've just briefly touched on crash dump analysis using WinDBG to analyze crash dumps, connecting host and target systems together. You're going to find a lot more details about that in the Debugging Tools help file. The Debugging Tools are a free download from Microsoft.com. Just go to the Microsoft homepage and search for Debugging Tools. Make sure that you have the latest copy because they update the tools quite frequently. You can also find more details in our book, Windows Internals. The last chapter covers crash dump analysis techniques, and our video on crash dump analysis will walk you through many of these scenarios and more, including advanced techniques for manual crash dump analysis.
Let's talk about some of the errors you can encounter after the system's booted and you're going through the logon process. And these types of errors can manifest themselves as hangs, as error messages that Windows or other applications present to you, or as a crash. One of the errors that might be occurring on your system that you might not even ever realize is that one of the automatic start services or auto start drivers is failing to start. And you're not knowing about that because by default Windows on client systems, professional systems, and home systems is configured not to pop up a dialog box that tells you one or more drivers or services have failed to start. That by default will only show up on server systems. So what we recommend you do to see if you're actually encountering that kind of error and might not be aware of it is to go into your Windows System Event Log. And you can do that by going under the Administrative Tools, Event Viewer, and going into the System Event Log, looking for a red indicator that there's an error like that, although I don't seem to have any one or more drivers or services failed to start errors, and identifying the particular driver or service that might be encountering your error, investigating the cause of the error, and then fixing the error.
Now, it's helpful in diagnosing problems during the logon process to understand exactly what happens when you do log in. So when you press Control-Alt-Delete on the keyboard, that keystroke sequence is processed by WinLogon, the logon process, which then presents the logon dialog. And the default logon dialog captures username and password, could also be using smart card authentication, sends that password and username to the local security authentication server process, LSASS, on your system. Now, LSASS may have to perform further operations like pass that on to a remote domain controller for authentication. So whether it's a local account or a domain login, LSASS, if the proper password and username combination was entered, returns back to WinLogon a data structure called the access token, the security credentials that represent the user logging in. WinLogon uses those credentials to create your initial process, and from that initial process, all the rest of the processes come to life. That initial process is userinit.exe. Many think that it's explorer.exe. In fact, userinit.exe is what by default runs Explorer. Now, if we go to the registry key, HKey local machine software Microsoft Windows NT, current version WinLogon, we'll find a registry value underneath called userinit. So let's go look at the registry editor, and we'll go up to HKey local machine software, go down to Windows, HKey local machine software Microsoft, Windows NT, current version WinLogon, and on the right we see a number of registry values that affect the logon process. The one that's referenced first by WinLogon is userinit, which if we zoom in we can see is set to userinit.exe. There is a comma, if you look closely, following userinit.exe, and it is possible that other programs can be added to this key. In that case, WinLogon will create userinit as a child process followed by the other processes listed there. Once userinit starts, it performs some setup, runs the logon script if configured, and then eventually runs the shell. If you go up, if we look back at the registry editor, there's a registry value called shell, and the default shell, of course, is explorer.exe. By the way, you can reconfigure the shell. If you don't like the Explorer GUI, you can run CMD, you could run a Unix shell, you could even run Solitaire as a shell for that matter. Explorer.exe, the default shell, then starts, and Explorer.exe has yet another set of registry locations that it looks at for things to start, and also folders like the startup folder.
There are literally dozens of locations called Windows extension points where the operating system or add-on components to Windows like Explorer or other applications go look to see if there's other things that they should load or run. Most of you are probably familiar with the tool that was introduced in Windows XP called msconfig. I'm going to run msconfig by going to the Start Run menu and typing msconfig. And the tab that's related to startup problems is over here on the far right, Startup. What you see here is a list of some of the components that are configured to run automatically when I log into this machine. Unfortunately, msconfig doesn't give us a whole lot of information about the items that it does show us here. For example, AGR MMSG. It doesn't even tell us where that image is located, much less who made it and what it's for. So msconfig stops a little short, and that's where a tool from sysinternals called Autoruns picks up. I'm going to launch Autoruns here. And what Autoruns does is scan any of a wide number of locations looking for entries that specify automatic start items. It categorizes the various auto start locations and places the items that belong in that category under various tabs. So you can see, for instance, here's the logon category. And the logon category corresponds most directly to what you see in msconfig. If we go to the Explorer tab, we see items that are configured to add on to Internet Explorer, like protocol filters or protocol handlers, setup installed components. If we go to Internet Explorer, for example, we see the infamous browser helper objects that are configured on this system. There's scheduled tasks, auto start services, any driver that's not disabled is shown here. Items that execute at boot time by Session Manager. We talked about that earlier in this presentation, that AutoCheck is one of the default configured images here. AutoCheck is the boot time check disk utility. Image hijacks, app inits, known DLLs, WinLogon, UI host and notification DLLs, WinSock providers, print monitors, and LSA providers. And I wish Autoruns didn't have to show you so many locations, but the fact is malware is getting very sneaky and tricky about where it configures itself to automatically launch, hoping that you're using a tool like msconfig, for example, to go look for them, because you're not going to see them. For example, here on the Everything tab, where Autoruns consolidates all of the other tabs into one view, you can see an entry that we didn't see when we were looking at the auto starts in msconfig, an entry that looks troublesome. It identifies itself as a virus. It looks like it's a built-in part of Windows. It's got actually an icon that is similar to another component inside of Windows, and even identifies itself as Windows NT Logon Helper application from Microsoft Corporation. Well, the fact that malware these days is trying to pretend to be from Microsoft to blend into the background, and that this view is just an overwhelming amount of information. Autoruns has a couple of options that help you zoom in on things that might have been added after the system was installed and might include malware that is causing you problems. Those two options are here. First, verify code signatures and hide signed Microsoft entries. And if I do another scan with those options in place, Autoruns will only show us items that haven't been digitally signed by Microsoft. We can see, unfortunately, that on this system that includes a number of items that are from Microsoft, and I've verified are legitimate Microsoft images, like these protocol filters that are part of the .NET runtime. Microsoft has not digitally signed these yet. I'm hoping that they will at some point. But now the list is a little bit more manageable. Now here, this definitely stands out as problematic, and it's not verified from Microsoft. Just like these other locations that are not verified by Microsoft, but we know to be from Microsoft, what we can do to investigate this further, because we might not be familiar with it or have ever seen it, you can right-click and then do a web search to see if any other people have come across it or an antivirus company has identified it as being malicious. By default, the search engine's Google, and what Dave and I do before we go to Microsoft is we be politically correct, so we go to the options menu and change the search engine to MSN Search, so that when we show up on campus to do a demonstration here, that they don't start throwing stones at us. Another way to look more closely at one of these auto start locations is to look at the properties, which Process Explorer shows you a subset of down here at the bottom of the display. You can see it tells you the timestamp on the image file and what the version number with it, the size, which might be relevant to distinguishing this malicious image from one that's legitimate. And you can even go to the location where this item is configured in the registry or the file system. So if I select Jump To, this is going to open regedit up, which we've got running already. So let me pull regedit, and it's going to have taken us right to that registry value where logon help is configured. So we could go in there and see if maybe there's command line arguments that might distinguish this as a malicious application. Finally, just like in MS-config, you can both delete items or you can disable them. So if you're not sure or you believe that an item might be interfering with the logon process or the boot process, you don't want to get rid of it altogether, you can simply disable it, try rebooting or relogging on, and seeing if the problem goes away. And one way to keep track of changes to your AutoStart configurations is to save the list to a file, and once you've saved the list and you subsequently do scans, you can compare the current scan with the previously saved scan by going to the File menu and doing a compare. Compare will ask you to point it at a previous scan, and any items that are new and as of the current scan will show up highlighted in green, allowing you to zoom in on stuff that's changed since the last time you might have done a scan.
This is just a great tool, Mark, and it's really amazing to see how much information that it exposes on AutoStart locations in Windows. But this GUI tool isn't really usable in a network environment where a system administrator might want to go scan all these AutoStart locations across all the workstations or servers on the network. Is that possible?
Yes, that's possible because when you go download AutoRuns from sysinternals, the zip package actually contains within it this GUI and an equivalent command line tool called AutoRuns-C. AutoRuns-C has command line switches that let you specify which of these AutoStart categories you want it to dump information for, to omit the signed Microsoft entries and check for signatures, for example. And you could even run this on remote systems using the PSExec tool from sysinternals, which we've seen and used in this presentation to launch applications in the local system account. PSExec was really designed to launch applications on other machines. So you would specify a remote machine, specify AutoRun-C, and specify a switch that causes PSExec to copy AutoRun-C to the remote system, capture that back to the local system in a file, for example. And the file, you can even specify AutoRun-C to output in tab delimited format. So you could then pull that information into a database and then keep a collection of your AutoStart locations across machines in your enterprise, run SQL queries against them to look for malicious applications or signs of abnormal activity.
And I know one of the things you added to PSExec a while ago was the ability to specify a text file with a list of computer names. So you could develop your own in-house list of computers, workstations, and or servers to scan, and in a single PSExec command, go run AutoRun-C on all the workstations and servers in your enterprise. So with a tool like AutoRuns, we can see that if you're facing errors during the logon process, this will be one of the first things you're going to want to run to try to do an inspection. Do you recognize everything that is starting when you sign in? Is everything explainable? Should everything be there? If not, try disabling the AutoStart locations that you think might be causing the problems to isolate the issue. And if that solves the issue, you've eliminated an error during the logon process. However, if you're still having errors that are not explainable by simply inspecting the AutoStart locations, you may want to engage another pair of sysinternals tools that are considered the Swiss Army knives for application troubleshooting, and that's FileMon and Regmon. FileMon and Regmon are tracing tools, FileMon tracing file I/O, Regmon tracing registry accesses, and in many, many cases, it's either file misconfiguration or missing files or registry data that's missing or misconfigured that is the root cause for strange error messages or failures in any application, including ones that may be started during the logon process. One very common issue is permissions problems. Files, folders, or registry keys that are locked down so that they can't be accessed by an application. This has been such a common problem that Mark and I run into that when we use FileMon and Regmon and get a capture of I/O activity, we'll first look at the log for access denied errors before we go then try to interpret what's actually going on. In FileMon, you might look for file not found errors, files that are missing somehow, or accesses to files that are occurring in a strange way, reading at strange points in the file beyond end of file. All of these could be clues to corrupt files that are causing other applications to fail.
Now, one of the problems with running FileMon and Regmon to try to diagnose problems that are occurring during the logon process is that it might not be possible using the standard AutoStart locations to configure them to launch early enough to capture what's going on. If you simply run them as well and then log off and try to log back in and hope that they're running, they won't survive the logon process because, like all other processes that are running on the interactive desktop, Windows terminates them during the log-off rather. So to get FileMon and Regmon running such that they can survive the log-off and then monitor through the subsequent logon, you need to run them in a different security context. One security context that PSExec makes it very easy to run these tools in is the local system account. So I'm going to open a command prompt and show you the launching of Regmon, for example, in the local system account. So I'm going to launch PSExec, type -S to have it launch in the local system account, type -I to have its GUI appear on the interactive desktop. If I omitted the -I, Regmon would still run, but we wouldn't be able to see it because it would be on the service's non-interactive desktop. And type -D to have PSExec launch the process and then return immediately to the command prompt without waiting for that process to exit. Now I'm going to specify the path to Regmon and enter the command. And now Regmon's appeared on my desktop, but it's actually not running in my security context. It's running in the local system account. And if I bring up Process Explorer, we can verify that by finding Regmon here in the process tree, which is down here, double-clicking, going to the Image tab, and seeing down here that it's running as NT Authority System, the local system account. So now if I were to log off at this point, Regmon would remain running, would disappear from the desktop, but when I log back in, it would reappear and have captured everything in the meantime, and then I could diagnose the cause of the problem that I was after.
One other slight variant of what Mark said is configuring FileMon or Regmon to start at system boot time. So versus using PSExec, configuring FileMon or Regmon as a service, an interactive service, so that when the system starts, they begin running. That could be useful to perhaps track down errors during the boot process, later parts of the boot process, as well as the login process. That could be done first by using the Serve Any service, which is part of the Windows Resource Kit tools, or you could manually create a service to run the command prompt to launch FileMon or Regmon, and the command prompt process will exit, FileMon or Regmon will remain, and in that way you've got FileMon and Regmon running even before the first logon.